Good day, ladies and gentlemen. This is the last lecture for this chapter where we're going to look at sign and magnitude integers. So we're going to do addition and subtraction for integers in sign and magnitude representation. And it might look quite complex at the beginning, but I'm going to try and make it simple for you by using lots of colors. So hopefully you will understand that much better then. Okay, so we have for addition 4 different combinations of signs, 2 signs each of 2 values, and for subtraction 4 different conditions. Now these different conditions we will look at in the algorithm just now and say a little bit more about them. So this means that we need to consider 8 different situations or combinations in total. However, if we first check the signs, we can reduce these cases as shown in figure 4.7. But before we get there to the figure, let's do some quick revision for sign and magnitude. Recall that for sign and magnitude, when we consider 4 bits, so for this case it's basically 4 bits, the leftmost bit, or the 1 bit from the left, that is the sign. So when it is 0 it means positive, and when it is 1 it means negative. So the remaining 3-bit number, that is known as the magnitude. Alright, so in the simple example here, I took figure 3.6 again just for some revision here, which again is a 4-bit representation here, and therefore you can see each of the first bits. So for this first part of this matrix here, everything starts with a 0, which indicates that these are all positive numbers, as you can see. Where, for example, 5 here, the 0 means it's positive, and the 101, if we convert that to binary, gives us 5. And so for the negative values, we basically start with a 1. So everything that starts with a 1 here indicate that it's negative. And for example, 3, the last 3 bits, 0, 1, 1, gives us a 3, and the 1 a minus, so therefore it's minus 3. Alright, so that's for 4 bits, and then just to generalize it to 8 bits, for example, here's just an 8-bit representation. For example, the positive value 0 looks like this, the positive value 1, 2, and so on, up to a maximum of 127, because 127 is the maximum positive number, because the first one is the sign positive, and then if everything else are ones, then basically that's the maximum number. If you convert those 7 bits to a decimal value, then it gives us 127. And then similar to the others, starting from the first negative number. Just by the way, remember that sign and magnitude is there is not actually a 0. Well, there's a negative 0 and a positive 0, as you can see. So there's a bit of a redundancy, and we know that there's actually just 1 0. 0 cannot be negative. However, this is one of the weaknesses of this system. Nevertheless, so there you can see for this particular one over here, 1 is negative, and the rest of it represents 1, negative 2 in this case, up to negative 127. And again, same explanation as above. The left bit is the sign, the remaining 7-bit number, that is known as the magnitude. So the sign is 1 in this particular example, and the magnitude is that. So again, the sign is 1, and the remaining 7 bits, that's the magnitude. So there is a simpler formula as opposed to figure 4.7 to only deal with addition, which we're going to look at in just a while. Just some notation here in the example that will follow, well, in the diagram that will follow. We will basically have the general structure of R equals A plus B. In other words, result is equal to A plus B, where A is the left number and B is the right number. We just distinguish between the left and the right, or the first and the second number that we need to add in this way. So typically, when you have a scenario where you, for example, have addition, so you want to add positive 17 to negative 22. So if we convert these to its corresponding sign and magnitude value, so minus 22, for example, because this is a minus, then basically that is represented by the 1, and 22 is represented by the remaining string. Same with 17, the positive is indicated by a 0 and the remainder is indicating 17, and the negative there is indicated by the 1, and the remaining 7 bits represent 5, as you can see. So indeed that makes sense. If you take positive 17 and you add negative 22, then basically the result will be negative 5. So as we said, A is the left number and B is the right number. And then we're also going to distinguish between the signs. So if we talk about AS, in this case, AS refers to that 0, which as you can see there is 0. And BS is the sign for B. So in other words, it's that 1 over there, which is the sign for B. And then the magnitudes, as you might have guessed, also indicated in the colors here, just so you can see. So the yellowish color here is the magnitude. So coming from the top there, it's this number. And also the magnitude for B, basically that blue number over there. And so the results sign over here is basically the one that comes from there, and the result magnitude is basically the one coming from there. Alright, so that's just a matter of notation. So don't get a fright. Let's look at the next formula, or flowchart rather. So as you can see, the idea here to do sign and magnitude addition or subtraction is basically by the very simple formula, the result is equal to A, that's either adding or subtracting B from it. Alright, so now the algorithms start as follows. We first determine what is happening there. Is it going to be addition or is it going to be subtraction? If it is subtraction, then basically we take the sign of B and we complement it. In other words, we flip it. So if the sign of B, whatever B was, if it was a positive, in other words, if it was a 0, that sign now becomes a 1. If it was a 1, it becomes a 0. The next thing that needs to happen, and by the way, if it wasn't subtraction, if it was simply addition, we basically then just skip that step and we continue next. And now we say, okay, now we need to determine the final sign. And the final sign is going to be determined, and that's S, it's going to be determined by taking the sign of A and XOR that with the sign of B. Alright, so remember what XOR does. XOR is the so-called difference checker. So if the first value and the second value differs, in other words, if AS was 0 and BS was 1, or AS was 1 and BS was 0, then a 1 is the result. Otherwise, If both were 1 or both were 0, the result would also be 0. Right, so then that's the next thing we do. The next thing is to determine the sign. So if the sign is different, now in other words, if the result there of this XOR operation, if the result is a 1, then basically we're going to follow this route. If the result of that sign determination was a 0 in the XOR, we follow that route. Okay, so if it was a 1, then basically what we will do to get the result magnitude is to basically say, let's take A's magnitude and get the 2's complement of B's magnitude. All right, and then if there was an overflow, in other words, if in the end, when we did this positive calculation, or this calculation, this addition here, and there was a carry that falls off on the left-hand side, in other words, we're following this route here, you'll see in the example just now, then simply we take AS, or the sign of A, to become the sign of the result, and then we stop. Right, so at that stage we would have the result's magnitude by that calculation, and we will have the result sign building up the total, the final value of the calculation. If there was no carry, all right, so if it was no carry, we will have to follow this route, and then we basically say, well, the magnitude result is going to be the 2's complement of the actual result. So we take this, the result that we currently have, and we basically take its 2's complement, and that becomes our new results magnitude. And for the result sign, we simply take the sign of B, and then we stop. Tracing all the way back now here. So if we got to this stage where we did the XOR between the signs of A and B, and the result of that was 0, then we simply do an addition of the magnitude of A and the magnitude of B, and that becomes our results magnitude. Again, if there was at this stage something that a carry that overflows, then it's at this stage where we have a real overflow. In other words, that means the value we were trying to store is larger than can possibly handled by the number of bits, and then in other words an overflow is reported and we stop. Otherwise, if there wasn't an overflow, it means the calculation did not carry things over into an overflow, then simply we take the sign of A, and that will become the result sign. So therefore we will now have the results magnitude and sign, and that is our value, and we stop. So you can see this rather looks complex, but all that this is, or all that this means, is that you'll have to study. You will just simply have to study this entire diagram by heart, because that is the algorithm that you will need to know when doing sign and magnitude addition and subtraction. However, the next slide I'm going to show you all of this a little bit more simplified and in words, and you can also study that to help you with this calculation. So here it is. So basically we take A as the left number, B as the right number, and this is just some revision over here. We already did that on about 2 slides back, to say AS is the sign of A, BS is the sign of B, That is the magnitude of A, magnitude of B, and the results sign and the results magnitude. Okay, so if we follow that algorithm, the first step, if we are subtracting, that's the special case, we first have to flip B sign. In other words, we have to do a complement on BS. So the sign of B, if it was 1, it becomes 0. If it was 0, it becomes 1. In other words, remember B over there, it will have a sign, so it's that sign that changes when we're doing subtraction. Alright, and then we do the XOR. We XOR the two sign bits. In other words, we take AS, the sign of A and the sign of B, and we XOR them. And then we go and calculate the result. If the result is 0, it means that they are the same. It means the sign of A and the sign of B would have been 0, or the sign of A and the sign of B would have been 1. Right, so it's that case. If it's that case, then we're going to simply do an add on of the magnitude of A and the magnitude of B, and use the sign bit of either A or B, because remember, in this special case here, they will both be equal. Both will either be 0 or either be 1. So it doesn't matter which one we take that as the sign. Okay. So then if it was the other case, in other words, in this example here, if the XOR resulted in a 1, in other words, if they were different, if the sign of AS or BS was different, then we're going to not just add the magnitude of A and the magnitude of B, but add the magnitude of A to the 2's complement of the magnitude of B. Right, so we first do a 2's complement on B. If there's a discarded carry bit, so the carry bit you'll see in just a while, if something falls off or overflows, then in this case it's fine. The addition result is used as is, and it gets the sign of A. But if there was no discarded carry, then there's no overflow, and the result is 2's complement of the addition result. So we take the result of what we calculated over there at the top, and the result is, and then we take the 2's complement of that. But okay, so to make this a little bit more easy, or to look at how this works, let's do the examples. So in this example here, we have two integers A and B. So, and they are stored in sign and magnitude format. So we're going to show how B is added, specifically added to A. So the operation is add. So here is A. A is that 0, 0, 0, 1, 0, 0, 0, 1, and B is this value over here, 1, 0, 0, 1, 0, 1, 1, 0. Immediately by looking at this first value of A, that's the sign of A, so we know A is a positive value and we know B is a negative value. So if we go and calculate actually what is the value of that, then basically simply converting it to binary, we look a little bit low down, we'll see that will result in a value of 17. And if you look at this value of B, that converted to binary, you'll see below in the red here, that will be negative 22 because B is a negative number. Right, so let's see how the calculation works. The operation is adding. All right, it was given to us over here. All right, so we know it's adding. So we can skip step 1. because step 1 said if it was subtraction we do something else, but now there's normal adding, so the sign of B is not changed. Alright, so B's sign remain 1 as you see it over there. The next step was to go and get the XOR between the sign of A and the sign of B. The sign of A, as you can see there, is 0 over here, and the sign of B is 1 over there. So, because they are different, XOR is a difference checker, so the result will be 1. Okay. Now, what we need to do next is to do the calculation of the results magnitude. And to do that, because we're at this specific stage where the XOR result was 1, then we know we can't just simply add the magnitude of A and the magnitude of B. We must add the magnitude of A and first the 2's complement of the magnitude of B. Alright, so how does that look like? So basically here we have A exactly as we brought it down from the top over there. Alright, and then we need to calculate this, the 2's complement of B. So we're just going to quickly do it here. So I'm over here now, and to simply quickly do a 2's complement of the magnitude of B, we basically can start from the right and we start copying until we get a 1. So we copy the rightmost 0, we copy the 1, and then we stop. The rest of the bits we simply flip, so that becomes 0, 1, 0, 1, 1. Alright, and that we see here is basically this result that we see over there. Exactly that result. Right, and now we do a simple addition between these two numbers, and if you go and do the addition below, I'll quickly show you. So here's AM, the yellow one, and already the calculated 2's complement of B, so exactly those two numbers. If we do addition here, we basically need to add 1 and 0, so 1 plus 0 gives us 1. 0 plus 1 gives us 1, 0 plus 0 gives us 0, 0 plus 1 gives us 1, 1 plus 0 gives us 1, 0, 1 gives us 1, 0, 1 gives us 1. No carries in this entire example, as you can see. So the result of the magnitude that we have is over there in blue, same as you see over there. But now, since there is no overflow, that part of the tree, if you go and look at the algorithm, no overflow happened. In other words, there was no carry or something over here that overflowed. So we need to take the 2's complement of the current, actually the current result, magnitude result. So in other words, that one, this one over here. So we take that one and do a 2's complement. So let's do that. So we start copying, we copy the 1 and we stop. From now on we just do flipping, so a 1 becomes a 0, 0, 1 and so on. As you can see, the flipping happened over there. And now basically we take the sign, is the sign of B, in other words BS, which basically, as you can recall from there right at the top, is still 1, and then basically the sign is negative. So in the end, if you had to write if you have to say final answer, then basically you will take this 1 and you write it down, and the rest of the result magnitude, which is 0, 0, 0, 0, 1, 0, 1. And there you can see it's 8 bits from here up to there, and that's your final answer. Okay. Let's look at the next example. In this example, 423, we have two integers a and b, similar again, but now this is a here, and that's b over there. But now b is subtracted from a. So let us see. If we follow the algorithm, we will say the operation is subtraction, therefore we have to do step 1. Step 1 says b sign, or the sign of b, we take the complement of the sign of b. In other words, remember, b's sign was 1, and therefore basically the complement of 1 is 0. So now basically the sign of b, I see I have it the other way around. If you basically had it like bs, small s, that's also acceptable. In fact, this is the more acceptable way to do it. So if you want to correct my slide there, you're welcome to do so. But basically, yes, b's sign now becomes 0. Just because of the algorithm we followed. Alright, step 2, the next step was to go and get the XOR of AS, or the sign for S, and the sign for B. Okay, so, and we know now the sign for A is 1 over there. Therefore, it's over here. And the sign for B, we changed over there. So the sign for B is now 0. And XOR between 1 and 0, it's a difference checker, so the result will be 1. Okay. And now because the result here is 1, we can't just do addition now at this stage of A's magnitude and B's magnitude, but the addition of A's magnitude plus the 2's complement of B. Alright, so there's the original A. I'm not going to do it over again. Here's the 2's complement of B. So it's basically taking that number over there, this number over here, and making it in 2's complement, which would yield in the result over here. And if you do that calculation, you'll get to this result. So let's quickly see how that works. So here you can see is A's magnitude and the 2's complement of B's magnitude already computed, and then we do the addition. So 1 plus 0 gives us 1, 0 plus 1 gives us 1, 0 plus 0 gives us 0, 1, 1, 1, 1 plus 1 gives us 0, and there is now this carry of 1, which basically is now going to fall off. Okay, now since there is an overflow at this stage due to this carry, we will simply take this result, or the magnitude result. We don't do anything further with it. Sort of is contradictory. You would have thought that if something carries, you must do anything special. It's just the other way around. As you recall in the previous example, there was no carry, and then we had to first go and calculate the 2's complement of the results magnitude. But now in this case, if there is this carry, then basically we don't do anything further. We simply take this as the result. But we must also just take note of the sign of the result. What's the sign of the result going to be? According to the algorithm, the sign of the result is the sign of A, which is 1 in this case, and there you can see it's 1. So basically, again, if you had to write down the final answer here, you would basically take that 1 and just write down the rest of the result. And those 8 bits is the final answer. And in this final answer, seeing that 1, it's a negative value, basically, which is that negative value. and if you do a conversion, a simple binary conversion of that, you will get to the value here of 59, negative 59. And basically, if you would go and do this calculations, you'd have seen that this is an example where we had negative 81 subtracting negative 22. So that basically effectively in mathematical terms means minus 81 plus 22, which gives us minus 59, and which is shown in the result below. I'm going to do one more example. So this is my own example. I've taken the same numbers, but I've changed it basically that these two numbers, A and B again there, you will notice now both of them are positive at this stage. All right, so, and we are just the kind of what's the right word? The kind of sum you want to do is addition, or the kind of I forgot the word now. Sorry, you know what I mean. So the operation, here I've got it. So the operation is adding. So according to the algorithm, the operation is addition. So again, step 1 is simply skipped. The sign of B is not changed. Right, so everything stays as it is. Step 2, we get the XOR between the sign of A and the sign of B. So we know the sign of A is positive and the sign of B is positive. So the result of the XOR there will be 0. And therefore, because the result here is 0, in the previous two examples, this result was 1 when we XORed A's and B's. But now in this case, it is 0. Therefore, we don't have to do a 2's complement of B's magnitude. We can simply take AM and add BM, and then if you see basically the yellow number is taken from there and the red number taken from there. You'll see in this case nothing has changed. We didn't do a 2's complement there because of the algorithm. And if we just do this simple addition here, we can say 1 plus 0 gives us 1. 0 plus 1 gives us 1. 0 plus 1 gives us 1. 0 plus 0 gives us 0. 1 plus 1 gives us 0, carry 1. And 1 plus 0 gives us 1. And 1 plus 0 gives us 1. Sorry, there's no carry over there. Sorry about that. Just ignore that. It's a typo on my slide. So, but in the end, you can see there's no final carry after you've done this result. Let's just do it again so you can believe me there's no carry. All right, so 1 plus 0 gives us 1. 0 plus 1, 1. 0 plus 1 gives us 1. 0, 0 gives us 0. 1 plus 1 gives us 0, carry 1 over there. Then 1 plus 0 gives us 1, no carry. 1 plus 0 gives us 1, no carry. All right, so there, if there was a carry in this case, then it would have meant that my final result is larger than 127. Remember, in this 8-bit case here, we technically only have 7 bits to represent, and we know by now that 127 is the biggest. So if it was a number or a result bigger than 127, you would have seen carries over here. But this was not the case, so everything is fine. There's not an overflow taking place here. So therefore, the result sign is basically we take the sign of A. Sorry, this is wrong. This is a typo on my slide. There is A's value here, as you can see, its sign is 0, right? Not 1. Okay, so therefore we know, we can see there the sign is 0. So the final answer for this would have been 0, 1, 1, 0, 0, 1, 1, 1. Right, and that's it. So this ends off chapter 4, and so now we've done enough calculation. Take note that we're not going to do addition and subtraction of real numbers. We used to do it in the past, but now that's moved to the appendix and we're not going to do it now. So no addition and subtraction of real numbers, just addition and subtraction of integers. Right. Enjoy your time. Thank you very much and stay safe.